Aloha. This is a lecture on the topic of scanning for the course Programming Language Theory, or ICS 313, which is a class in the Computer Science Department at the University of Hawaii at Manoa. Scanning is the first step that an interpreter or a compiler takes when turning your program into something that can actually execute and run on a computer. So we're going to go through the basic concept. So the idea of scanning is to go through a text, a program, a string, which is really just a list of characters. You're going to go through that list looking for interesting things and group those things into chunks. Now you've got a list of chunks. What do we mean by chunks? Well, that depends on exactly what you're doing. If you're a word processor, chunks are words. It counts the words. Those are chunks. Those are things interesting to a word processor. Your compiler, however, is looking for a wider variety of things. Keywords, symbols, names, numbers. Those are the chunks. And the compiler is going to arrange those chunks into patterns in order to turn it into an executable program. Scanning is just the part that goes through the chunks. In order to understand what we really mean by this, though, we're going to look at a concept called formal languages. Formal languages is the deep theory part of programming languages, but also of computer science in general. This is what connects computer science in a very deep way to the way things work in a very broad sense. So let's start with some of the things that we've discussed in programming language theory, which is types. We've talked about types a lot. We've covered it in several chapters of the textbook. We've talked about denotational ways of talking about a type, where we say that a type is a set. That is covered in chapter 7 of the textbook, which is Programming Language Pragmatics by Michael Scott. This is something that we see a lot in pure functional programming languages. We can also talk about types as a structured collection of things, of values. This is covered in depth in chapter 8 of the textbook. System programming languages like C and C++ really focus on data arrangements. This is the approach to types that they take. Finally, we can talk about abstraction-based approaches to types, where a type is meant to abstract, be an abstraction of a range of possible values. This is described in chapter 10 of Scott's Programming Language Pragmatics, and is really something that sees its full flower in object-oriented programming. But we're going to go back to the set approach, denotational approaches to types. So that means we need to talk about what a set is again. And a set, which you may remember from courses in high school, maybe middle school, even grade school, a set is a collection of things. And you can ask, is this thing in this set? Yes or no? That's membership. You can create new sets from two sets. If you've got one set and a second set, you can take their intersection, which is a new set, consisting of only those elements that are both in the first set and in the second set. Or you can create a union, which is a new set consisting of any thing that is in both the first, that is in either, not both, either the first set or the second set. You can construct sets as well by simply listing the items that are in the set, all the things that are in the set. So you can create the set my dogs by listing the three dogs that are my dogs, Comet, Quachi, and Star. You can also create a set by describing a rule for how to make that set. Intersection and union is an example of rules that tell you how to make a set from two other sets that you already have. But you could also have an arbitrary rule that creates a set by describing what elements are in it and what elements aren't. So the set all even positive integers, that is a set. It's one we're familiar with. It but it's just a rule. We're certainly not listing every element in that set. It's infinitely long. We couldn't list it all. And we can create a new set by using that rule union and taking the union of all even positive integers, one set, and another set that's all odd positive integers, and get a new set which is all counting at integers, both the even and the odd. Any number that is non-zero and positive is in this set. And we built it by describing a rule. So now let's talk about a particular kind of set. Start with an alphabet of characters or symbols. That's a set. All the characters, all the symbols in that alphabet form a set. We'll call that set A. Now, let's talk about strings of characters in A. So pick a character from A, followed by another character from A, maybe the same one, maybe a different one, followed by another, again, maybe the same, maybe different, in any combination you want. The empty string is an element of this set, but every single element of A is a one element, one length list that is a string of characters in A. But so is every pair, every triple, every quadruple. If we have n different characters in A, then for a length k, there are n to the k strings of exactly that length. This is easy to see with the empty string. There's only one because n to the 0 is 1. It's easy to see with length 1 because there's n single character strings. And similarly, it's easy to see with strings of length 2. There's n squared strings of length 2, and so on and so forth for any particular fixed length that you want. Now, let's take that set of all strings of A. We'll call that set S. Now we're going to create a new set called a formal language, and we're going to call that set L for language. It is a subset of S. Could be exactly the same set as S, could be the empty set, could be something in between that contains some of the strings of A from S, but not others. Very simple set concept here. There's no semantics, no meaning to this language L. The only thing we can do with it is ask, is this string in this language or not? So now I want you to think about a tricky little question. Is this question, are you in this language? Is this string in this language? The same as the halting problem formulated by Turing and others. And the halting problem, if you don't recall, is given a computer program, will this computer program stop? And remember, in general, you can't decide that. You can't look at a general program and know this program is going to stop, or no, this program will never stop, except by actually running the program. But there's a problem with actually running the program. If it stops, you know the answer is yes. This program halts, this program stops. The answer is yes. But if it doesn't stop, you don't know whether the answer is yes, this program will stop, or whether the answer is no, this program will never stop. All you can possibly know is that the program hasn't stopped yet. And that's the halting problem. And that's the question of decidability. You can't decide whether a program can stop. But how is this related to the simple membership question of, are you string in this language, yes or no? Well, that gets to the question of how do you define what that subset L is of S? If you create L through a rule, that rule could be arbitrarily complicated, or that rule could be very, very simple. And if that rule is complicated enough, that gets you to the halting problem. Simply trying to run the rule is like running a computer program. And so the question, is this string in the language L, is decidable or not? In general, it's not decidable because it is equivalent to the halting problem. But what if we had very, very simple rules? If it's simple enough, we know it's decidable. If the rule is simply this contains only single character strings, it is absolutely decidable. Is it still interesting? And that will get us to the next segment of our lecture.